Good morning, everyone. As our numbers rapidly increase, I'm just going to give you my, usual spiel to get us settled in to the morning. And today is a very special morning. It is the last keynote presentation of our workshop. It's kind of sad, but also, a little bit of a relief maybe for those of you who are overwhelmed. So today's featured photo, at least one of our participants will recognize this photo. In fact, the one person who will recognize it is the person who took it, who's here. I have verified. If people want to guess who took this photo in the chat, you're welcome to. It was taken in Crater Lake in 2013. The photographer kicked the camera by mistake during this long exposure, and that is what gives it this crazy ripple effect. And looking at the stars shining through the dark tree trunks, I think it's just absolutely beautiful. If you look closely, almost in the center there of those trees, you can see the Andromeda Galaxy for you M31 aficionados. And Marcus says Aurora, obviously. Yes, Aurora, our keynote speaker for today, is actually an accomplished astrophotographer, which I figured out trying to hunt down some info for her bio, and I was particularly impressed by this one. Beautiful photograph. Another beautiful photograph is the conference photo that we took on Tuesday. However, a few people DM'd me and said, oh, I wasn't in the photo for whatever reason, my video wasn't working, I wasn't there, blah, blah, blah. They want to be in the photo. You'll get your chance, but I hope that you're studying this photo right now because you will be tested on this. And the question is, are you in this photo or are you not in this photo? That's it. That's all you need to know. Are you in this photo or are you not in this photo? Hold that information in your head, okay? You're going to need to hold that information in your head for the next 10 minutes. Are you in this photo is the question. All right. Study it carefully. All right, so tonight at 4:30 p.m., we have a social hour. And this is kind of like a way that we can celebrate our time together at the workshop. It's informal. You don't need to download anything in advance. Details on Halo 21, socializing. You know that it's going to be cool because of the very edgy way that room is spelled. It's an unstructured video chat over drinks of any kind. It's going to be awesome. I'm not going to go into detail. The details of this are in Halo 21 General. 12 of you have already filled out the Google form, and I thank you from the bottom of my heart. Thank you, thank you. This kind of assessment is important. There's one non-anonymous survey and one anonymous feedback form. Both of them are absolutely essential. Please do them. Please, please, please don't make me beg you. Don't make me say this over and over again. Head to Halo 21 General and see the details. There's links for both forms. You just gotta do it. And it's how you submit your mandatory activity reports. So you won't get bugged if you do it. 15 minutes or less. All right, more new results. Just yesterday, Yu Guang Chen posted a new video on KBSS using foreground and background galaxy pairs to trace the structure and kinematics of the CGM H1 at Redshift 2. Amazing video. These new results videos are still coming in, and I am just so pleased to be able to recommend them to you. So please head over to Halo 21 New Results or go to our YouTube channel and watch these incredible videos that really are telling us about the future of the CGM and our ability to understand it. Finally, I just want to point out that these are the photographs of the people who are frantically trying to prepare their debriefs for tomorrow. We'll hear from Halo 21 Emission, Halo 21 New Instruments, and Halo 21 Parametric Model. I know New Instruments, we had a roundtable discussion yesterday. That was 2 hours. It could have gone for 4 hours. It was absolutely amazing. It's not too late to head over to these Slack channels and check out what's been going on. Mark has been furiously preparing slides for the Halo 21 parametric model share back tomorrow. It's sure to be very, very interesting. I know that I have found myself in the position of having to defend all observers. He tried to put observers in the corner, and nobody puts observers in the corner, as far as I'm concerned. All right, and finally, I just want to plug emojis. For those of you who have not yet adopted them, when we're not communicating in person, we're not in the same room, we miss out on physical signals that suggest agreement, approval, connection, and warmth. Emojis are the fluid language of the internet, and they will help us fill that void. There aren't right or wrong ways to use emojis. Add nuance, add your own flair, confound people if you want. With that said, today's panel discussion is actually going to take place totally in emojis. All right, that's a joke. See, I can't tell that you're laughing because nobody's using emojis, but I assume you are laughing hysterically. All right, so just kidding, but I do encourage you. Thank you, Grant. Thank you, Camp. Gosh, you guys are. All right, so, but go ahead and use emojis, especially as reactions in the Slack channel. It's really going to help me guide the discussion in the direction that you want the panel discussion to go. It'll help me read your reactions. I can't do this. We're not sitting in a room together. Emojis are great. I've also just heard that Ben and Aurora have come up with an emoji that they want to symbolize X-ray, and it's the skull, not the skull and bones, which you can see on my frequently used emojis there. Don't use that one. That's like death. But the skull is the X-ray symbol, the plain skull, and they're going to post that in the Halo 21 Week 8 Future Obs Slack channel. All right, and finally, I am absolutely delighted to introduce our keynote speakers today. We've got a double header. First up, we're going to hear from Dr. Aurora Simionescu. She's an astrophysicist on the tenure track at SRON, Netherlands Institute for Space Research, and also an affiliate member of the Kavli Institute for Physics and Mathematics of the Universe at the University of Tokyo in Japan. In addition to her spectacular astrophotography, you may know Aurora as an expert in the physics of the hot plasma and galaxy clusters. Next up, we will hear from Nick Battaglia, a professor at Cornell University who specializes in the thermal and kinetic Sunyaev-Zeldovich effect and what it can tell us about galaxy evolution and cosmology. He's directly involved with the Atacama Cosmology Telescope, among many other projects, and with any luck, they'll both be finished around 9 a.m., give or take. You know, I'm not strict about these things. We'll take a quick break, and then we'll have a thrilling panel discussion featuring Dr. Alexei Viglinin, Rachel Somerville, Edmund Hodges-Cluck, and Colin Hill. An absolutely all-star lineup today. I cannot wait. We're going to spend now, I told you there would be a test. So before I let Aurora take the reins here, we're going to try the workshop photo attempt number 2. Now remember when I told you, you have to know whether or not you were in that photo, okay? If you were not in the photo on Tuesday, for whatever reason, but would like to be in the photo, turn your video on right now. If you were in the photo, and this, I promise you, this will really help me out when I try to assemble it later. If you were in the photo, please turn your video off. Zoom will organize it so that the video off people are all at the end and the video on, so I can actually easily add you to the photo that we already took on Tuesday.
All right, week 8, everybody. It's been really exciting. I've been listening to this through the ears of an X-ray astronomer, and I have a slogan of the conference that I would like to share with you, and the slogan is "Hot is where it's at." And by that, I mean not only that most of the baryons that we are looking for are in the hot phase, in the CGM, but also that is where most of the action is happening. And I swear I came up with that before Chris Martin said the exact same thing on Tuesday, so we agree. And if you would like to understand and to know where all of these baryons are and what they are doing, more importantly than that, to probe this more than 10 to the 6K phase, you have two choices. You have the choice of X-rays, either in absorption or in emission, and that's what I will be talking about, or you have the choice of the Sunyaev-Zeldovich effect, and for that, stay tuned for Nick's talk just after mine. Okay. One thing that hasn't been stressed to the extent that I would have liked to have seen it stressed, though, in this conference, is that if you go to the hot phase, the other thing that you learn is how everything connects. And in week 5 from Dushan, I think, we have seen this amazing plot of this intergalactic transfer. These are things that fly out of a galaxy and end up in another galaxy after having traveled through the cosmic web. So we would really like to understand also how all of these things connect. So the outskirts of clusters of galaxies, intergalactic large-scale filaments, and the CGM, these are all things that should equal us, should be of equal interest to all of us who are in this room right now. So the holy grail of this, the thing that is going to put the theorists out of business, or perhaps into business, would be to create a map that tells us about the thermodynamics, metallicity, and kinematics across this entire range of scales, from CGM, from scales related to feedback, all the way out to the cosmic web. And as we've heard already on Tuesday, if you want a map, it's the easiest way to take picture of a lion, as much as you can do it, is through emission. So let's see how far emission studies actually take us. Now, for the people in the room who are not X-ray astronomers, I got this question a couple of times. What is it that we are actually looking for in emission in X-rays? What do things look like? So here is a plot for 3 different temperatures of the gas. So this is the spectral model. This is for a 10 to the 8th Kelvin. So this is a very hot cluster of galaxies, about 10 keV. This is 10 to the 7 Kelvin. So this is more like 1 keV. Either the outskirts of a cluster of galaxies will typically have these temperatures, or a typical galaxy group. And here you have 10 to the 6 K. And that is, I think, what most people here are interested in. 2 things very important that you should keep in mind throughout this talk. The first thing is we keep saying, oh, you know, emission depends on the square of the density. This is true, but in this picture, actually, emission also, the flux also depends on the temperature. You can see the shape is changing, and it depends on the metallicity. And Mother Nature has actually been a little bit kind to us in the sense that cooler plasmas for a fixed density and a fixed metallicity are actually brighter. Okay. The other thing you should keep in mind is that when you look at these very hot things, most of what you are seeing in emission is hydrogen. That is most of the flux. But when you look at cool things, most of what you are seeing is lines. Okay, so a really important thing, what we are seeing in X-rays for these very low temperature plasmas is just the metals. If you care about hydrogen, go to Nick's talk. Okay, there's a lot of fine print here for you to look at later. But these are the spectra that we're interested in. And now, what kind of observational characteristics do we need a telescope to have in order to reveal these things? I've picked out 4 important things that you want your telescope to have. There are many other things, but I don't want to make this plot very complicated. So these things are effective area. Things are very faint. You need a big mirror. Grasp, things are not only very faint, but they're very big on the sky in some cases. So you need a big mirror and a big field of view. You need a big survey speed. Spatial resolution, you know, there are a lot of physical details that are interesting on very small scales that we also care about. And you care about the kinematics, so you want to have a spectral resolving power so you can see the shifts and widths of your emission lines or absorption lines in X-rays. And so this is where we stand right now, Chandra and XMM. These are my units for each of these axes, and we'd like to push as far as we possibly can along each of these axes that we can. So as many axes as far as we can at one time. So let's go. The first push comes in this direction, and it comes from Eurozeta. The log axis doesn't do this figure justice. Eurozeta is about 4 times, has a grasp that is about 4 times that of XMM Newton. And we've already seen in week 4 from Marcus's presentation what that improvement of a factor of 4 can buy you in terms of mapping large-scale emission from the Milky Way and in terms of mapping large-scale emission from the cosmic web in this very deep scan of Abell 3391, 3395. Now, the full Rosita survey, All-Sky survey is underway. And one thing that I think you can look forward to is this proposal in a paper by Ben, which is that we can then take this All-Sky survey and we can pick out halos, CGM halos, we can stack them, and then we can see what we might get. So here are the predictions. This is from Eagle, and this is from TNG, both for high specific star formation, low specific star formation, and then high mass and low mass samples. And there are two important messages here. I think the first important message is that we can detect these things through stacking. We can detect these things with Rosita out to a few tens of kiloparsec. And the other thing is that you can start to see the difference between Eagle and TNG, and maybe we can constrain which of these things has a feedback prescription that fits slightly better to the data. Let's go in the next direction. So next up on the launch pad is CRISM, and this actually goes in the complete opposite direction than Rosita. So we have a very tiny grasp, but we have a very good spectral resolution. And this is actually due to the technical limitation. We are now using microcalorimeter pixels, and it's hard to have a very large array. So if you want this resolution, the first thing you have to do is start with a small field of view and a small number of pixels. All right, now this has a 7 eV resolution. It's actually optimized for hot things, okay? It will do great for clusters. For this iron 25 line, you have a resolving power of 1,000, but for these low energy lines, maybe not necessarily that much. If you want to know more details about CRISM, go to yesterday's tutorial by Edmund. I want to tell you 3 things that I'm excited about that CRISM is going to do. The first thing is my favorite object of all time, and this is M87. This is the BCG of the nearest cluster, the Virgo cluster. And we've seen in week 4, I believe, from Dylan, these beautiful simulations of how black holes were blowing metals out of a galaxy at redshift 1.8. Now, M87 is well, not an equivalent of that, but is a place where we actually are seeing the black hole transport metals, blow metals out of the center of the galaxy to large radii. And here is an abundance map. This is iron abundance measured with XMM Newton. And you can see here this plume of high iron abundance material. And this plume happens to coincide with this big radio lobe that is coming out of the black hole. So the radio lobe of the black hole is pushing or pulling, actually, I think, metals out to large radii. And even though at these low energies, we don't have the power to resolve the width of individual lines, what I think we will be able to do is use the line shifts and use the line shifts in order to see whether there is any line of sight component that is associated with this metal uplift of the black hole, and how fast is this actually happen. The other thing that I wanted to point out, because we are in the CGM workshop, is what is the lowest mass halo that we are guaranteed to get time from CRISM. So the lowest mass halo in the CRISM PV phase is NGC 4636. This is a giant elliptical galaxy in the outskirts of the Virgo cluster, very, very bright, beautiful signs of interaction with the AGN. And what we are hoping to do here, there is a hint from XMM Newton of resonance scattering. And this would indicate that the turbulent velocities are very low. And we would like to confirm this hint and get a much better measurement of the turbulence that is associated with AGN feedback in this galaxy. And lastly, I will not belabor this because Edmund went into detail, so please see his talk. M82, we've talked a lot about M82 in this workshop. We will observe it with CRISM, and we are looking for shifts of the magnesium line, silicon line independently of each other, see if these atoms are moving together or separately, line broadening of the hot iron 25 line, because that one is resolved. We're looking for charge exchange, and we're looking for the chemical composition of the wind ejecta. So lots of wonderful things. Right. So this is going to be the next 5 years. I'm going to fast forward now to 10 years from now. And 10 years from now, we're looking forward to Athena. Athena will carry 2 instruments. We'll have the XIFU. The XIFU is here in blue, and you see what a giant leap the XIFU is going to be compared to CRISM, that is here in yellow. And also Athena will carry a wide field imager, and the wide field imager is here in orange compared to eROSITA. So Athena will be better than eROSITA and CRISM combined into one telescope. It's going to be absolutely amazing. Now, again, the spectral resolution is optimized for hot clusters. Okay. And so in these hot clusters, you can measure kinematics to an amazing precision. And because now you have a much better spatial resolution and grasp, you finally have a true integral field unit. So these are some models and predictions. Again, our friend M82 here at the top, and the other, favorite poster child Perseus cluster at the bottom. These are predicted X-ray images. And from every pixel that is about this size of this square here or this square here, you can get amazing spectra that will tell you about the dynamics and the chemical composition of these things. This is amazing in nearby objects, but also the capabilities that you have now will allow you to study evolution up to redshift of 1 of the metal content, of the kinematics, and so on and so forth, of these objects. Now, Athena was actually not built on the science case of the CGM. And I dug and dug and dug for some predictions that would be able for me to answer the question that I know that you guys have. And the question is, what will Athena do for the CGM, and how far into the CGM can we possibly go? I didn't find a publication, but I did find a participant of this workshop who happens to be next door to me in Leiden, and who was kind enough to share with me work in progress, and made sure to tell you that this is preliminary and you should really take it with a grain of salt. So here we are. These are so first of all, in color, the lines are predictions from the Eagle simulations for the brightness of some representative lines in X-rays. Okay, so this is 07, 08, neon 10, and magnesium 12. And so for different halos of different mass, you can see the median or the mean predictions for the brightness of these lines. Here you see the limits that you can get with CRISM. So with CRISM, you can get down to flux of about this much. And here you see the limits that you'll get from the XIFU. And the long and the short of this is that if you are interested in 10 to the 12, so L-star kind of halos, with XIFU, you can get to, again, a few tens of kiloparsec. If you really push it, you can go to maybe 100, but that's going to be quite difficult. But this is for individual emission lines 1 by 1, and this is a 5 sigma limit. So if you combine detections in many different lines, you can go, I would say, easily to 100 kiloparsec, but beyond that would be a little bit hard. Okay, so that was Athena. I want to tell you there is one more mission on the horizon that I have been told is now an official project of the Chinese Space Agency. And this is going to be amazing. So Hubs basically goes in this parameter space I was talking about to a different trade-off. The trade-off is that Hubs has the exact same number or a very similar number of pixels as Athena, but instead of pushing for spatial resolution, they have pushed for very large survey speed. So this is by far the highest grasp mission that is a microcalorimeter. So you could study, you could survey big parts of the sky with the resolution of a microcalorimeter. And Jiang Tao here has a very nice plot that shows you why it's important to do that, because the line emission from the CGM, it's very important to have this resolution to disentangle it from emission lines from our own galaxy. So I think for the CGM at very, very low redshifts, this mission is going to be the thing to watch out for. Right. Now we're getting into, a little bit less certain terrain. We are all awaiting the results of the 2020 decadal survey. And actually, I haven't heard Axis mentioned at all in the Future Observations channel on Slack this week. And we should talk about it because Axis is actually could be quite exciting for the CGM. The main point of Axis is of all of the imagers I've talked about so far, Axis is the first one that actually has Chandra resolution. Everything else would have worse resolution than Chandra that we're talking about so far. And it will have by far the lowest detector background. Now, detector background was not one of my 5 things because I didn't want to burden you with it, but detector background is very important for pushing things to very low surface brightness. So the goal of Axis is to push things to 50 to 100 times fainter things than the limit of Chandra. So if you want faint emission, you should be paying attention to this proposal. And the thing that is on everybody's radar that we have been talking about is LINX. And so this is proposed for 2036. LINX has, again, kind of like Athena, it has 2 main, well, a third one I will talk about in a minute, but 2 main things on board. One is a microcalorimeter. There's actually 2 flavors or 3 flavors, but let me talk about 2 flavors of this microcalorimeter. One is the main array of the microcalorimeter, and that is this purple thing here. The really exciting stuff for CGM science, though, is the ultra high resolution subarray of this microcalorimeter. And that is the yellow square over here. And that will finally put us into the resolving power of more than 2000 at 08, okay, at the lines that are bright in the case of the CGM, the dominant emission lines of the CGM. So we can finally do dynamics of the CGM in a spatially resolved way with this ultra high resolution subarray. And then the high definition X-ray imager, this is a CCD, so it doesn't have great spectral resolution, but it will have the spatial resolution of Chandra with, of course, a much larger effective area and survey speed. I don't have time to tell you how many amazing things LINX is going to do, but hopefully Alexei Viklinin will be with us today and he's on the panel, so please direct your questions to him. What I want to leave you with in terms of the emission, where I want to conclude, is this plot, and this is a product of collaboration initiated during this KITP workshop, and so we've been discussing this with Ben, John, and Nastasia, and the credit goes to Ben for producing this wonderful plot that compares the same simulated halo as it would be observed by Chandra, Erosita, Athena, Whitefield Imager, and LINX HDXI, and this is a 10 to the 12.4 log of M200. M200 is 10 to the 12.4. And the redshift 0.01, and all of these are 100 kilosecond observations. If you're not an X-ray astronomer, this is about 1 day of time. And this is how our view of the CGM in emission is going to evolve over the next sort of 15, 20 years. Now, even though we are getting really further out in radius, you can see all these beautiful details. Nevertheless, we are all aware that eventually emission gets too faint. And if you really want to push to virial radii of these halos, you probably also need to do absorption. So let me spend the last 5 minutes of the talk telling you a little bit about what we do in absorption. So again, introduction, where we are right now is this side of the plot. So these are observations of bright X-ray point sources with the XMM Newton RGS. And these are O7 absorption lines from our own galaxy. Okay, this is Milky Way absorption. And basically, these are about 1 week of staring at a single point source. And in 1 week of staring at a single point source, you can get a log NO7 of about 16. And that's what NO7 of 16 looks like when you look at it for a week. Now, where we would like to be is more like maybe 15. So these are again predictions from Nastasha for this is O7 in absorption from Eagle. And if you want to look at the virial radius of a 10 to the 12 solar mass halo, you need to be around here. Okay, so 10 to the 15. If you want to look at more than a single line, if you want to catch not only O7, but some of the next 3 brightest ones, then 08, neon 10, and iron 17, you would need to go even below 10 to the 15. Okay, so that's our goal, 10 times better. How are you going to get 10 times better? With current instrumentation, the only thing you can do is stacking again. And I want to show you this very nice result from Kovac and collaborators. And what they did is they used the Chandra LETG spectrum. And they looked at this guy, you know, telephone number, age something, and they know that there are 17 Lyman alpha absorbers within a certain distance of this point source that we're looking at in X-ray. So what they did is they took the observed spectrum with Chandra and they blue shifted it 17 different times to the corresponding redshifts of those 17 Lyman alpha absorbers. And they stacked the spectrum 17 times, well, different parts of the spectrum 17 times, and they report about a 3 sigma detection of O7 absorption. That is what you see here, and that corresponds to log NO7 of 15. So we are where we want to be, but in a stack, not in individual systems. If you want to do better for individual line detection, not for a stack, you need new toys. And here is a cheat sheet for the new toys that I think are on the horizon. And let me explain the axes here. So here is the resolving power, and I'm plotting this for rest frame 08. For rest frame 07, you should probably move the circles a little bit more to that side. What we have here in red are microcalorimeters, in blue or white are gratings, and the solid symbols are approved and the empty symbols are proposed missions. And here what you are seeing is the figure of merit for weak line detection. So this is how efficient, how much more efficient one of these missions is compared to the other ones if what you are looking for is weak lines. Now, you want to be over here, right? Because we don't, so the higher you are on this axis, the more efficient you are at just finding the line, saying, hey, there's a line here. But you also want to measure dynamics from this. You also want to measure dynamics from this line. Okay, and so if you want to easily resolve 100 km/s line broadening, you need to be in the green regime. So this is where things stand. You know, this will be available so you can stare at it later. Let me give you some numbers for these proposed future missions, what they can do for you. We've heard Randall say several times that Arcus is planning to probe in a 2-year mission 30 lines of sight to get 100 O7 detections down to 3 milliangstrom. So this is basically the outer part of a L-star halo. If you look at Athena XIFU, we have 2 objectives. The first objective is to find, well, WIM filaments, but honestly, this could just as well be the CGM in absorption. 150 detections towards BLX and 50 detections towards bright GRB afterglow. So that gives you 200 detections of these emission lines. And the other objective, which is very interesting, is that towards these GRB afterglows, once the afterglow has faded away, you can stare at it and you can detect the same gas also in absorption. So that would be very cool. And then we have LINX, and LINX will observe 80, the goal is to observe 80 AGM to characterize the hot halos beyond the virial radius in 30 galaxies with a mass around, again, L star. So these are the number of detections that you might expect. This is really beautiful plot from the LINX concept study report that you can also stare at. And so the limits for LINX are this black contour over here. So out to this contour, you can detect absorption lines, and that is going to be, of course, really amazing. One plug slide for a really crazy thought and proposal that I submitted to the ESA 2050 voyage. So I'm now taking us not 20, but 30 or 40 years into the future, which is this proposal to have it all. Okay, so to have really huge effective area, really good spatial resolution, excellent spectral resolution for these low emission lines, and 1 million calorimeter pixels, 1 million spaxels for this detector. What we would like to do is to do a survey in emission, and in the survey will be sensitive enough to go to the virial radius of an L star halo as part of the survey that will cover 1,000 square degrees. And the other really crazy thing that you can do is that you can detect things in absorption, but not in absorption against point sources, but in absorption against the cosmic web, against the X-ray background. Okay, so you can take any point source out of the X-ray background. You have a bunch of point sources in your field of view no matter what. You can stack all of them, and you will be detecting absorption from the cosmic web at the same time as emission. Really crazy thought for the far future. So I'm out of time, so I want to leave you with my summary, and my summary is a compilation of all of these ranges of parameter space that we are hoping to probe in the near future. And what I would like to see in the discussion after that is we have this huge parameter space opening up. I think we should be prepared for surprises, and I would like us to discuss what we think those surprises might be. So thank you very much.
Thank you so much, Aurora. I have so much to be inspired by right now. That was absolutely excellent.